So let's talk about the rest of the semester. So we've finished the Gauss-Bonnet theorem, which is really the highlight of the course in terms of the homework and the standard material. And now we're in the bonus material. And to me, that's where it gets very exciting. Now, but before we proceed to bonus material, you guys had a homework last week that was due on Friday. I think it was a decently challenging one. Does anyone have like a question on the homework or like to discuss it, or something that you don't have to? But in order, this is your last chance. But you can always discuss after class and whatever. But anyone have a topic that they really like to have revisited? Yes.
I guess, like, broadly speaking, for geodesic curvature, like, how could we see that appear on the final? Like, what would be like the types of questions that could be asked?
I think that's a good question. To me, conceptually, what is geodesic curvature? It's d theta dt, or d theta ds, right? It's the rate of change of theta with respect to s from the point of view of the end, right? So, in other words, zero geodesic curvature is, if you're on a potato, I don't care how lumpy it is, if you're trying to walk in a straight line, that's zero geodesic curvature, right? So now, what conceptually, what does that mean? What zero geodesic curvature means, that's the first thing to understand, right? Is that it means that when you parameterize by arc length, your acceleration vector, which is, let's call it beta of s, right? Beta double prime of s is perpendicular to the surface, right? So you're not accelerating in the tangent plane of the surface at all, right? You're only accelerating in ways you can't control. We call that normal curvature, effectively. It's the normal curvature. Really, it has to do with the potato, right? But then let's suppose you choose to turn to the left, turn to the right. Well, okay, now you have a component of the acceleration vector which is not perpendicular to the surface. And since it's a unit speed curve, it will be perpendicular to your direction. So you're either accelerating to the left or accelerating to the right. And then the only question is, well, how much are you accelerating to the left or the right? Well, we have formulas for that. Okay, but what is it intuitively? It's d theta ds. And when you measure theta in radians, right, which is the natural set of units, right? So whatever d theta ds is, the rate of change of your angle that the ant perceives, right? That's what motivates the formulas you have in the book.
Sure.
Does that make sense? Yeah. Okay, that's the conceptual. Now, in terms of problems, I'll refer you to my practice final exams. Okay. Because I don't remember. I'm just trying to think off the top of my head, like what would be a good problem. The Gauss-Bonnet theorem. Be ready for that. That's obviously a really cool result. In fact, let me show you all a fun application of the Gauss-Bonnet theorem really quick. Okay. So let's, and this is one of my favorite final exam problems as well. So let's say that we have a flat R2. Okay, so this actually is like the XY plane, for example. It goes off infinitely in every direction. Okay. Now, what is the Gauss curvature of the XY plane? Anyone tell me? Zero, right? It's flat, right? Its principal curvatures are both zero. So K1 equals K2, K1 equals K2 equals 0. Or is it kappa 1? No, kappa 1 and kappa 2 are both 0. Those are the eigenvalues of the shape operator, right? The shape operator is 0. Okay. But now, let's suppose that I take a large disk in the middle, and I cut it out. Now we have a hole there, right? And then what I want to do is fill in with anything else you like, any other surface you like. Okay, so inside that large disk, you put in any metric you like. I think my artwork there wasn't too good. Let's just try a little better. Okay. So what we're going to do is we're going to put in, inside this disk here, we're going to put in some metric. Here you can see it's like a bag of gold, the way I did it, right? You got the shape there? Mm-hmm. All right. And but I want to do this in such a way. So fill in with let's say topologically trivial. In other words, I haven't changed the topologically equal, trivial meaning the same. I haven't added any handles or anything. Surface with Gauss curvature greater than or equal to 0. Okay? Gauss curvature is greater than or equal to 0. Okay. Now here's the theorem. Ready? Theorem. Now then, let's call this surface now M. It's two-dimensional surface M. Theorem. with these hypotheses, M2 is precisely flat everywhere. In other words, so what this is saying is, like you cut out a hole, you fill in however you want with scalar curvature gradient equal to, Gauss curvature gradient equal to 0, and it turns out there's only one way to do that, and that's to fill it back in exactly the way it was before. Okay, this is called a rigidity theorem. Right? There's no way to fill in with any other surface, any other metric. Okay, by the way, this doesn't have to be a subset of R3 even. This is an abstractly defined surface, right? It could be sitting inside any Euclidean, any dimensional space or none at all. And so this is like, oh, okay, that's a pretty cool geometry theorem, isn't it? The only way to fill in with non-negative scalar curvature everywhere. And by the way, we want to fill in smoothly, no corners. What's that?
With a smooth boundary.
Yeah, it has to be, no corners here, yeah. Because like if you had a corner there, then that's not zero Gauss curvature. Okay. So now how do we prove this? Proof. By the way, I don't think you even need this topologically trivial assumption. I just put it in there to keep things simple for us right now. So let's what you want to do is apply the Gauss-Bonnet theorem to this surface here, to this disk D2. Okay. Now remember, I said it's topologically a disk. So this circle here is the boundary of the disk. Okay. So D is this topological disk that goes out to this circle. The boundary of the disk is a circle. Okay. And it's just write down the Gauss-Bonnet theorem. So we have the integral over D of the Gauss curvature times the area form plus the integral of the boundary of D of the geodesic curvature ds, right? This equals 2 pi times the Euler characteristic of a disk, which is 1. So it's 2 pi. Does everybody understand that that's what the Gauss-Bonnet theorem tells us in this study? It's the Gauss-Bonnet theorem for a disk. Okay, and so if you stare at this, you realize that, wait a second, what is this integral of the geodesic curvature ds? Well, this is just a circle in flat R2. Remember we said you can't change the metric way out there inside the circle. At the circle you're not changing anything. And so let's say you're not changing anything even in the neighborhood of that circle. Like, go in a little bit, you're still not changing it, right? Because we had to match up smoothly, right? So I know what the geodesic curvature of a circle radius r is. That's just going to be 1 over r, isn't it? And I know what the circumference of a circle radius r is as well. It's 2 pi r, right? So this distance here is 2 pi r all the way around, right? The circle. And so this right here is 1 over r times 2 pi r. So this gives me a 2 pi here as well, doesn't it? Well, the 2 pi's cancel. It means the integral of the Gauss curvature is 0. But you said that the Gauss curvature has to be greater than or equal to 0. And so then this implies that the Gauss curvature is in fact identically 0. Okay. And so, and that's all I asked you to do is just show you it's precisely flat everywhere. So it turns out, by the way, if something has 0 Gauss curvature everywhere and it's topologically trivial, then it's just a flat metric in R2. I'll state that as a fact. I won't prove it. Right, but it's not very hard. It's annoying to prove, but it's true. Okay. So now, what if I get rid of this topologically trivial fill-in? Well, then this would be 2 pi times the Euler characteristic of the disk, right? Now, the Euler characteristic of the disk is, if I were to add some topology here, right? When I'm adding handles, you all see that? That means the Euler characteristic, every time you add a handle, the Euler characteristic goes down. So it turns out the Euler characteristic has to be less than or equal to 1. So that's a little bit of a sophisticated thing. We can get into that in a little bit, okay? But it turns out if I allow it to have topology, the Euler characteristic is less than or equal to 1. And so that means that this is less than or equal to 2 pi. And so this becomes right here less than or equal to 2 pi. And the argument stays the same. right? So that means the integral of k dA has to be less than or equal to 0, but you said k is greater than or equal to 0 everywhere, so k is identical to 0. Okay. So actually, there's no way to fill in, even with topology. And so that to me, this is actually I love this theorem because it's actually pretty easy to prove, right? It's an immediate consequence of the Gauss-Bonnet theorem, right? And so it shows there's a rigidity here. This also has physics content, by the way. It says physics content. It turns out the Gauss-Bonnet theorem in this context here is can be used to say something else. Okay, so here let's do this. You know, so if we let's rework the Gauss-Bonnet theorem in the following way. Let's talk about cones. I want to do this. Okay, how about this? I won't even go there with the cones. Okay, let's just take something even simpler first. Let's take something that's exactly flat, but inside a circle, we'll have the metric just be whatever it is. Okay, that's yeah. So a little bag of gold there and other stuff. Okay, whatever. Okay, I mean I don't know. It's hard to draw these things. Anyway, some arbitrary metric there, but otherwise it's exactly flat outside the circle. Okay. Flat R2. And so if we look right down the Gauss-Bonnet theorem, it's saying that the integral over the disk, let's say this is the whole thing, we'll call it M2. So if I integrate, I want to look at the integral of k dA over the whole M2, okay? Let's talk about that quantity. Well, we know it's 0 outside the disk there, right? So this is the same thing as the integral over this disk region here, right, d2 of k dA, because I'm assuming it's exactly flat out here, right? With the integral of k dA, this is equal to, by the Gauss-Bonnet theorem, it's going to be, let's suppose everything's topologically trivial again. This is, in fact, going to be 2 pi. Again, we're going to have equality here, so it's 2 pi minus 2 pi. It's going to be 0. Okay. So now here, here's the theorem. Another way to draw the theorem is now let's not assume that k is greater than or equal to 0. The point is, you know, if M2, or how about we could do it? Say, if M2 is topologically R2 and flat like R2, you know, flat metric on R2 outside bounded region, then the integral over the whole thing, M2, of k dA equals 0. Okay, so, you know, it's saying that, you know, you can have some negative Gauss curvature over here, but you're going to have to average out with some positive Gauss curvature over there. Fair enough? And then you can see that this other thing we proved is a corollary. That's because if you say k is greater than or equal to 0 everywhere, then k must be identically 0 everywhere. So let me give you now a physical interpretation of this statement. Okay, this has physics in it. Because you see how it's flat at infinity? You don't remember that Einstein said matter curves space-time? That's the concept behind general relativity. Well, someone once asked me, what is general relativity in lower dimensions? Like, you know, there's a basic principle in mathematics, which is when you take something complicated, you should always look at the easiest special case of it, right? So if 3 plus 1 dimensional spacetimes are complicated, then, okay, what about 2 plus 1 dimensional spacetimes? What about 1 plus 1 dimensional spacetimes, right? And if you say, but let's go to the 2 plus 1 dimensional spacetime case, you can think of this two-dimensional surface as a t equals 0 slice of a 2 plus 1 dimensional spacetime. Okay? And the fact that everything is flat at infinity means you have 0 total mass in your system, right? So we have, think of a 2 plus 1 dimensional spacetime, but let's say all the interesting stuff is going on in some finite distance from the spatial origin, right? So once you get, there's a center, right? A center line, the t-axis, right? So as long as you're within a certain distance of the t-axis, then that's where all the matter is, and everything else, we want it to be perfectly flat. But if it's perfectly flat away from the central region, then what that means is there's no gravity, right? That geodesics aren't curving towards the middle. And so that means this represents something with 0 total mass. And so, that's weird. Okay, so you have something where the total mass is 0. Well, how do I get that? Well, it turns out K represents energy density. And this is saying that the integral of the energy density in your system is 0, and that's why the total mass is 0. Okay. And so, so this is what could be a segue into general relativity. Let me just go ahead and get more precise. There's a precise example of a metric I should show you so that I can make sense of what I just said. That's all by analogy there. So let's go ahead and just get precise. And let me show you the Schwarzschild spacetime. And so qualitatively, just draw in a cylinder here. And then you've got other slices here. And a slice up here too, I guess. Okay, so what we're doing is we have a t-axis that goes like this. Okay, time is going up. But then we also have an x-axis. A y-axis and a z-axis. I'll have y and z share the same axis because I don't have enough dimensions. So I'm trying to draw a picture of a 4-dimensional space. And if you're wondering what does that cylinder in the middle represent, I just want to point out that this is not a circle here. That's actually an S2, right? Because it's sort of a circle in 3-dimensional space, right? X, Y, and Z. So that's actually a sphere. Okay. So everything is 1 dimension higher than is drawn. Right, this is actually R3 here, okay? And then you take R3 cross R, that's R4, or R31, same thing. It's a space-time, okay? And what I want to do is put a metric on this. And there's a couple of different ways to express this metric. Let me do the one that I think I like the most. Yeah. So what's the metric there? Well, the Minkowski space-time, that's something I mentioned before. By the way, it's not, everything we're about to do right now is not on the final exam. It's also not on the homework. So this is just for your education. Right? So you can just really enjoy it. Ask questions, enjoy learning, and learn about special and general relativity. So Minkowski spacetime is when you put a minus sign in the rule of Pythagoras. I think I probably mentioned that in the first week. Is that right? Okay. And I have a whole series of videos I really hope everyone watches, actually, for yourself. Just go to professorray.net, click on videos, click on special relativity, and watch those 15 videos, and then you'll understand special relativity. Yes?
So, I don't know if this is necessarily correct, but I interpret t that's time, correct?
It's the time coordinate. It's not time.
Okay.
It's sort of like, I just want to point out the difference between coordinates and physical observables. So coordinates are this practical thing where it's like latitude and longitude. It doesn't actually mean anything, right? So the t as a number doesn't actually mean anything, but it's just a coordinate. Now we want it to mean something, right? We're like, but wait a second, didn't Newton say, well, yeah, for Newton, t is time. For Einstein, t is only approximately time. As long as your velocity, by the way, you'll see exactly how how the sense in which it's close to time and the sense in which it's very much not time. And when I write down the metric.
Okay.
It's just a coordinate just like x, y, and z. So that's the thing about unification of space and time. Like, for example, if I said, how much x coordinate do you have right now? You'd be like, what are you talking about? Like, or even if I said, what's your latitude or longitude right now? You'd be like, I guess I could look it up, but why does that matter, right? So there's no physical meaning to it, right?
Yes.
It's just that we need coordinates because that's how if you've got a better idea, share it with us. This is basically what it comes down to. Like, coordinates are, the fact that we need coordinate charts to describe these curved surfaces is just because we don't know of any other way to do it, right? There's something unnatural about it. Like, why that coordinate chart? Why not some other coordinate chart, right? Why do we use the Mercator projection to look at maps of the Earth? Why don't we use some sort of other conformal mapping where Australia's really big or something like that, right? Which Australians love to do, right? Well, you can. They're all equally valid, right? And so, and this example will demonstrate that. Okay, so here's the Minkowski spacetime. You put a minus sign in the rule of Pythagoras. And I think I talked about null vectors and space-like vectors and time-like vectors, I think, right? And that minus sign has all kinds of interesting geometric implications. But for right now, I can tell you that's special relativity. So how do you go to general relativity? Well, the simplest example that's non-trivial, Schwarzschild. It's a Schwarzschild spacetime. I want to show you the way, if you were to go to Wikipedia, you get one metric that they will write down. I would prefer to write down in a different way. Because there's many different choices you can do. I think what I'm about to show you here is a little bit nicer. For the applications I have in mind anyway. But yeah, I think it's better. Okay, where r is just the radial coordinates, the square root of x squared plus y squared plus z squared. Okay. All right, so that is the Schwarzschild spacetime. Now I want to point something out. When m equals 0, it is the Minkowski spacetime. That's the first thing to understand. If m equals 0, you get 1 over 1 here. You get minus 1 squared. That's minus dt squared, right? And then this just becomes 1 to the 4th, right? And so you get this the Minkowski spacetime when m equals 0. But when m is positive, you get the spacetime for a non-rotating static black hole. Okay. And one can draw the picture of it right over there on the right. Okay. Now, you may notice that something interesting happens when r equals m over 2. This factor here becomes 0. And so this sphere over here actually is the coordinate sphere where r equals m over 2. Okay? Let's go ahead, by the way. I'm going to assume m is positive. Okay? That makes it a black hole. Now you might ask, what about when m is negative? I've actually studied that, wrote a paper on that one time with a co-author. And these are, you can call them sort of negative mass black holes, or I dub the term zero area singularity. These have never been observed in nature and are not thought to exist. Right? But however, when m is positive, it's sort of like, why don't we ever see negative energy density? Right? Well, it turns out general relativity doesn't mind negative energy density. You can talk about it all day long. But in the real world, all the particles seem to have positive mass or zero mass. So, okay. So therefore, we don't see negative mass black holes or negative mass planets or negative mass stars or anything with negative mass. So that's just, the general relativity doesn't say you can't have negative mass. It's other physics. It's just the experimental fact. So we take m greater than or equal to 0. This gives us what is known as a black hole. There's something weird happening, you can see, because this factor in front of the dt squared goes to 0. And r equals m over 2, right? And so we know, in fact, that is the event horizon of the black hole. Okay, it's the point of no return, as it turns out. But this example allows you to understand what general relativity is talking about. What's going on here is, and I think I must have written down the Einstein equation, right? G equals 8 pi t, right? G equal 8 pi times T. This is the Einstein curvature tensor. So for right now, I'll just call it curvature. But that's a matrix, right? Think of it as I think it was like a 4 by 4 matrix at each point. This T is also like a 4 by 4 matrix at each point. They're called, these are both called two tensors. They're symmetric two tensors. The reason they call them two tensors is that they're two-dimensional matrices. Right? Imagine a matrix has not only rows and columns, but also hyperrows and hypercolumns. So that would be like a 4 tensor. Okay, so the matrix is a 2 tensor. So this is like a 4 by 4 matrix each point, also call it 2 tensor. And this is the, think of it as matter density. It's called the stress energy tensor, but roughly speaking, it's matter density at each point. Okay, and so you set them to equals. This is how you make precise idea of matter curved space-time. Now for us, when we think curvature, what do we think of? Gauss curvature, right? So in our setting, when you say the Gauss curvature, oh, is that like matter density? Yes, and that, in fact, the answer is yes. In 2 + 1 dimensions, there is only Gauss curvature to talk about for a two-dimensional surface. And so, yeah, it turns out that's your matter density, right? And this is saying that the integral of the matter density must be 0 if you're flat out here. Okay. Now, why would that be? Well, let me tell you what gravity is in this setting. Okay, so we can do this with the Schwarzschild example. I'll tell you what gravity is. It's understanding what the geodesics are doing. Okay, because imagine that you have an ant walking on a potato trying to go in a straight line. Complicated path, nonetheless, right? Imagine you're a spaceship floating in outer space, far away from a black hole. You cut your engines off. Well, the axiom is that you will follow a geodesic. Right? That's a reasonable idea, right? Well, what are the geodesics? Well, it turns out the geodesics in the Minkowski space-time, of course, are just straight lines, perfectly straight lines. But for a Schwarzschild black hole, the geodesics, they curve inward a little bit. And the closer you are, the more they curve. Right? And so it's as if you have a force of gravity. In other words, if the geodesics are simply things, curves, where the geodesic curvature equals 0. Right? These are just paths where if you had to say what's the straightest thing you could do, right? That's what you're doing. Now, we've only studied geodesics in the context of a surface in R3, right? What's different here is there is no R3. So it's like this Zen exercise I could ask you to do is, visualize a sphere in R3, right? Okay, now visualize the sphere but without the R3. Right? And it's like, oh shoot, how would I do that? Well, actually, there's something to think about there, isn't there, right? Like, how do you do that, right? Okay, well, on the other hand, before I even tell you how to do it exactly, I think I've said it before, I want you to recognize that, yeah, I mean, the sphere does exist without the R3, actually. And I'll prove it to you because you almost never pull out a globe when you're trying to figure out stuff on the surface of the Earth. You ever pull out a globe? Do you need to see the globe in its full three-dimensional glory to understand what's going on? No. You usually look at two-dimensional maps on your iPhone, right? Or in the olden days, you get a world atlas out and you start flipping through the pages and stuff, right? Okay. So yeah, you don't need R3 to visualize the sphere, and you don't need a bigger space to visualize this. I've told you what the metric is. Told you, how to compute lengths, lengths. And by the way, this tells you what the dot product is, right? This notation means put a minus sign in the usual dot product. This says put a minus sign in the usual dot product, but also weight the time components when you multiply them by that factor, and the x, y, and z components when you dot product them, multiply them by that factor. Okay, it's going to just be distorting things by factors that depend on where you are. Okay, so the dot products get modified. That means lengths get modified, actually areas and volumes. Turns out this has all the information you need. If you understand how to take the dot product of vectors, then you understand everything about the geometry of the space. Get angles between vectors and everything. So locally, if you're just trying to go straight, you get geodesic. Well, what is a curve? Well, it's just going to be some crazy curve, right? Guess what? These are straight lines when m equals 0, and the larger m is, the more it seems to curve towards the middle. So you have to set back globally. See, locally, you're just going in a straight line, but when you set back globally, you're like, oh, shoot, that's curving towards the middle, right? And then that's what we perceive as gravity, as a phenomenon that the geodesics aren't straight lines in some global coordinate chart. Yes?
Is there like a progressive curve towards the middle, or does it kind of stay in like a circular type?
I mean, you get orbits and everything. In fact, here's the crazy thing. You ready? This is not only the metric for a black hole, it's also the metric for the solar system. So it turns out 99.8% of the mass of the solar system is the sun. So even Jupiter is small compared to the sun. So what we can do is the gravitational field of the solar system, to a pretty good approximation, is just the gravitational field of the sun. So let's just go ahead and do that. And so, well, guess what? The gravitational field of the sun doesn't change if you collapse it into a black hole of equal mass. Except, obviously, if you're in the vicinity of the sun, you can see things are different. Light doesn't escape, so forth, right? But the gravity is the same. And so if you took the sun and collapsed it into a black hole of equal mass, the orbits of the planets would not change. And so this is the metric for. So in fact, and what are the planets doing? And all the asteroids and comets, they're following geodesics. And so that's sort of a spiraling geodesic. So it's harder for me to draw, but yeah, they're spiraling around geodesics as well.
Gotcha. So the planets don't really think they're accelerating. They think they're going in a straight line.
They think that they are completely at rest. This is sort of the relativity part of it.
Right. Right.
And they are not wrong. We choose a coordinate chart. For example, let's try to understand the solar system. It would seem logical to choose a coordinate chart where the sun is not moving, right? And it stays at the center, and then the planets orbit around the sun. But you could also, if you wanted to understand the solar system, you could choose a coordinate chart. You could choose a coordinate chart where not only is the Earth not moving, it's not even rotating. You could do that if you wanted to. Now, it'd be a crazy coordinate chart. It'd be a total mess of a coordinate chart, right? And so that's one thing. By the way, sometimes you'll run across a novice, someone who, there's an interesting type of person. I wonder if you've ever met one, where they're pretty smart, actually. They have an IQ of 140 or better sometimes, right? But maybe, and they might even be 50 or 150, 160. They could be very smart, but maybe they don't have the education, right? Like it's really, really a lot of brain power, but maybe they haven't actually had the course, right? And so I've heard people, very smart people, say that general relativity is ridiculous because it basically says, well, why don't I choose a coordinate chart where the Earth is not moving and not rotating, right? And then doesn't that mean that the sun is going around the Earth, right? And then they would point to that and say, see, general relativity is wrong. This is absurd, right? The Earth, any fool can see that the Earth goes around the sun. You can't say the sun goes around the Earth, right? This is ridiculous. Okay, and so let me explain that just because it's like a kind of an interesting thought, right? You can choose a coordinate chart where the Earth is not moving and not rotating, and everything else is sort of spinning around, right? But that means your metric is going to be really messy and really complicated, okay? And so the mistake they're making is not understanding that there's a space-time metric that changes when you change coordinates, right? And it's so complicated, I don't even want to attempt to write it down. I guess I could if you paid me enough money or something, right? And so yeah, but strictly speaking, yeah, I could choose. You could choose a coordinate chart for we usually use the Mercator projection for the surface of the Earth, right? But you could choose any stupid set of coordinates you want. You could make the smallest. You could make Hawaii bigger than Alaska if you choose your coordinate chart, right? If you want, I guess you could, right? It doesn't mean that Hawaii is bigger than Alaska, right? So coordinates. So understanding that coordinates are just kind of sort of necessary things in the background. So what we're trying to, and anything that you do in coordinates is not physics. That's the thing. Anything that's true in the coordinate chart is not necessarily physical, usually not physical. Okay, so and that's the mistake in the error in the logic is just because you can choose a coordinate chart where the Earth is not spinning, so what? That's got nothing to do with anything. The question is, how do you define these things? You got to define things in terms of geometric. And so the key concept is what's physics is geometry. So any of the geometric quantities is what's physics. So, for example, let's go back to your question of what is time, right? Time is not that t coordinate. Time is the length of your world line. That's what time is. Time that you experience is the length of your world line. And so one thing that's interesting about that is let's consider this world line here. Let's suppose now what does this world line here represent? You're near a black hole, and but you're keeping a constant distance from the black hole, which means that you're being sucked in by the black hole, but you have thrusters on your rocket and you're resisting it, right? You've got your thrusters on and you're keeping a constant distance from the black hole. Or you can get really close to the black hole and do this world line. Now you're really close at that point, which means that light, even light cannot escape if you go a little bit further. So this means you have one hell of a rocket ship to be able to do that, right? That means that you're accelerating, quite rapidly, and you're playing with fire here. You're a daredevil, right? And okay, so by the way, I say quite rapidly. Why not? I mean, how rapidly depends on the mass of the black hole. If it was a really tiny black hole, maybe not so rapidly. Actually, there's a weird thing. If it's a really tiny black hole, then you'd be accelerating very rapidly. If it's a very, very big black hole, you wouldn't have to accelerate very much at all. And I'll tell you one thing that's kind of interesting about this is that the curvature of space-time at the perimeter of the black hole actually is smaller for big black holes than it is for small black holes. It could be that we just entered a supermassive black hole right now, by the way. It could be that the Milky Way galaxy just now fell into a black hole. Could be. If the black hole is the size, let's say size of the black hole is 1,000,000 times bigger than the size of the known universe. Okay? If it was something beyond our comprehension, right? It could be that we just entered the event horizon of some black hole that's so unimaginably big we can't even imagine it, right? It doesn't really matter. It's going to take billions of years before you hit the singularity of the black hole, or trillions or quadrillions of years before you hit the singularity of the black hole anyway, right? So, interestingly enough, it's the actual space-time curvature at the event horizon goes as 1 over the mass of the black hole, or probably actually curvature, 1 over the mass squared, actually, I think. And so the acceleration you're going to have to do to get away with it is going to go as 1 over m squared as well. Anyway, but nevertheless, you're having to accelerate more here because you're closer and less here. Now here's what's interesting. How much time are you experiencing? Well, let's suppose that you go from t equals 0 to t equals 1 in both cases, okay? Well, you come over here to figure out the length of your world line. Up here, if you go from t equals 0 to t equals 1, you each experience 1 unit of time. But here, you have to multiply that by this factor here without the square, because this is telling you how much time squared changes. And so, in fact, time changes by the square root of that factor, so without the 2 there. And notice that this factor is going to 0 on the event horizon. Remember, this event horizon where r is equal to m over 2. By definition, it's where this factor is 0, right? So this factor is 1 at infinity, and it's getting close to 0 here. So you're actually experiencing much less time when you're close to the black hole than when you're far away from the black hole. And that's what the content of this factor is telling you, is that you experience less time when you're close to the black hole. That was portrayed in a movie called Interstellar. Thank you. Did y'all see the movie? They go down to the surface of the planet. There's a black hole orbiting. There's a planet orbiting the black hole, and I'm pretty sure they went down to the planet just to demonstrate this fact. There's no other plot reason to do it, right? So they go down to check out the planet. They're there for like 20 minutes or something. Then they see a tidal wave or something, and they get the hell out of there, right? They go back to the spaceship, and it was 20 minutes for them, but it was what, years for everyone else?
Yeah.
Okay. I'm not sure if the numbers really add up from the movie, okay?
But
do they?
I think they really
yeah.
do.
Actually,
Okay.
no. The whole thing was like it was kind of an exaggeration, but like
Close
they
enough.
kept the idea there.
Yeah. I think the idea is basically right. Question, comment? Yes.
Yeah. So when you're talking about the idea that like you have geodesics,
Mhm.
when you're talking about a black hole, like in the context of R3, we always assume we were like on some manifold. Like what manifold are we on?
Okay, great question. You're asking the right question. Because what should be bothering you right now is that I keep on talking about visualize the sphere, but without R3, right? Well, then what is even a geodesic, right? Now, one thing that y'all showed, I think, in one of your homework exercises, is that geodesics have this sort of length minimizing property, right? In the sense that if you take a length they're locally length minimizing, right? So I can tell you, and so this is a fact. Geodesics, what geodesics are from your point of view so far is they're curves on the potato where the acceleration vector, a double prime of s, is perpendicular to the surface. That doesn't make any sense now. And so now we have to say, come up with a new idea of what a geodesic is, right? Because there isn't that extra dimension. But you also learned in a homework exercise that geodesics actually minimize length. Like if I take 2 points and then find the length minimum path between those 2 points, it always has 0 geodesic curvature. Okay. And another fact is you take any geodesic curve, even if you know, you could take here's the surface of the Earth, right? Take 2 points close to the North Pole. The shortest path between them, obviously, is to go around this way, right? Just the shortest path. But what if someone were stupid and went around the long way? Well, that's also a geodesic, right? But locally, it's still length minimizing. Globally, it's not. Obviously, this path here is not the shortest distance between those 2 points, right? But it is locally length minimizing in the following sense. Take any 2 points, like this, take any point, and then take any point sufficiently close to it, that's length minimizing. So it's locally length minimizing. In other words, in a small enough area of it, it's length minimizing. So now if we redefine geodesics to be paths that are locally length minimizing, right? Then, and actually I have to change something. Do you guys know the difference between a local min and a local max and a critical point? Right? A critical point just means the slope is 0. It could be a local min, it could be a local max, right? So because of this minus sign, it messes things up. So now instead of saying geodesics are things that locally minimize length, let's just say that geodesics are paths that are critical points for the length functional. Because actually, they locally maximize length when you put that minus sign in there, right? It's a little bit of a weird thing, right? But if I have 2 points in a space-time, right? 1 point here, let's say that, you know, we're in a space-time, just like I've drawn here. Say we're in the same picture, right? You would think that's the shortest distance between 2 points. But actually, if I go along the light cone and go like that, actually this has length 0, that has length 0, this has length 10. That's shorter, right? So actually, in fact, what's funny is that 10 is actually the longest way to get from here to here. Right, everything else is shorter. All right, so geodesics are locally length maximizing curves when you're talking about time-like curves in a space-time. Okay, so our intuition, things are just, but this anyway. Except, so, you know, our brains work in a certain way. It's hard for us to really fully get that. So you just have to remember some things are backwards from what makes sense to our brains. Yes?
So a question, we talked about light a couple times.
Yep.
Think about these geodesic curves, and so our planets are just following the geodesic curves.
Mhm.
But light seems not to have an issue escaping, you know, our solar system.
Yeah.
So
It's also following geodesics. They're called null geodesics.
okay. So
Yeah.
like, what rules is light playing by?
Well, I mean, the easiest way to understand them in general relativity is that they follow null geodesics. So, and there I have to admit, the definition of what a geodesic is, I have to give you the actual definition, which is, I can't rely on this locally length maximizing thing anymore, because the length of those paths are all 0. And, but there is a definition. You know, in fact, I'll go ahead and tell you what it is. What we realized was a geodesic, like if you have a potato here, right? And there's your ant, right? And the ant's following a geodesic, right? We realized that 0 is equal to alpha double prime of s, right? Well, that's not quite true. The tangential part of that, right? And then that actually equals the covariant derivative in the alpha prime of s direction of alpha prime of s. Do y'all remember that? Because this covariant derivative is means just the tangential part. And so that's alpha double prime of s, but didn't take the tangential part. Okay, so we did that, I think. And so we could say, in fact, in fact, that's the equation. This is the equation that is what a geodesic is in all cases. Now here's the problem. What the hell is the covariant derivative? Because we define that to be just get rid of the third dimension, right? Just take the tangential part. Well, we need to figure out how to define that now. And I'm going to show you. I'm going to show you, but that is actually not trivial. Okay, I have to show you something really super cool, but yet non-trivial to do this. Okay. And so I'm pretty tempted just to do it now. Gosh, but I don't think I quite have time today. Maybe we do it next time. Okay, I'll show you next time. So this really is the equation. So the equation of a geodesic is this. This is true for light. It's true for planets. It's, take a rock, throw it in the air. That's a geodesic. Right? It's not true for you right now because you're accelerating. You're not following a geodesic. Something's pushing on you right now. Can you feel it? It's your chair. Okay? You're in an accelerating frame of reference as a result. If you jump off a building, you will be in a that's a geodesic. Don't do it, please. Take a rock, throw it in the air. That's a space-time geodesic. Okay. Other questions? Okay, so things to do. What does that upside down triangle mean? What is this, right? What is this? How do you take the derivative of a vector field in the direction of another vector field? You have no idea right now how to do that if you're not in a submanifold of R3. Okay, you have no idea, trust me. Right? And this is like, and by the way, if you want to impress the hell out of me, figure this out before Wednesday, okay? But you could Google it, right? But I don't think it's very easy to do. I have to say, this is something pretty non-trivial I'm going to show you on Wednesday. I don't think I know anyone who figured it out themselves. Like, obviously someone had to figure this out the first time. And, could I have done it? Like, it's interesting. Like, I'm a mathematician, I like to come up with ideas, right? Could I have figured this out myself? Had other people not already done it? I like to think I'd have a shot, right? But it involved, I think the answer is, you got to really contemplate things deeply, right? Like, it's interesting what we take for granted, but we should not take that for granted. That is something interesting. Okay. Now, right now, what you do is you just express these as R3 vectors, and then take directional derivative of each of the components of the R3 vector, and then just take the tangential part, right? So, but what if there isn't a third dimension? What if your curved space is not sitting inside of a larger space, right? How do you do this intrinsically is actually highly non-trivial. All you have is a metric. Okay, so we'll do that next time. Yeah. And so this is what the Schwarzschild metric is. Let me show you some more pictures. Let's make a connection to this discussion we had earlier on, by the way. Remember when I said it's flat R2? Well, if you were to take a slice, right, a t equals 0 slice of this spacetime, notice that you get this Schwarzschild metric. There's a spatial part over here. If you set t equal to a constant, that means dt equals 0. Right, so if t equals 5 everywhere, the delta t is 0. So you ignore that. And so what I put in the box here is the three-dimensional metric. And what you can, and we can draw a picture of that. Just try to remember this discussion we had here before. I'll make a we'll be generalizing it a bit. And it turns out, and if you want a nice discussion of the Schwarzschild metric, go to my thesis. Just Google Hubert Bray thesis. All right? And because I had an introduction to my thesis, and I had some pictures in there. And I think, I'm not, it's something you might attempt to take a look at. So, what does that metric in the box look like? Well, I'll show you. If m is 0, it's just the flat metric on R3, isn't it? Right? So this would be an m equals 0 case. Now, you might say, yeah, but even if m equals 0, when r equals 0, I have 0 over 0. So you might just say, well, okay, really we should remove the origin, right? So let's go ahead and remove the origin there. It's not so well defined, right? But basically, it's flat R3. But now let's suppose m is not 0. I'll take m to be positive. Then you'll see that actually when r is big, this factor is 1. So we're not really changing things for r big, right? But when r is small, then actually this is going to infinity. Right? And so we're stretching lengths by a factor that goes to infinity. Right? And so actually so you think of this missing point here, what actually happens is you make the metric bigger here. It actually starts to blow up. And guess what? It blows up and you get another asymptotically flat end. It actually has symmetry. It has a Z2 symmetry to it. Turns out. Okay? And it turns out it's not that surprising that it has this E2 symmetry, because it turns out this metric here actually has 0 scalar curvature. Okay? Now, I haven't told you what scalar curvature is, but let me just tell you intuitively what it is. You all know what Gauss curvature is, right? Given and so what is, it's kind of like, it's a number at each point, just like Gauss curvature. But remember when I said that curvature is fundamentally two-dimensional? So let's say we're in a three-dimensional space. I can pick any two directions, and that defines a two-dimensional plane in that direction, right? So if you're in the tangent plane of a three-dimensional manifold like this, the tangent plane is just an R3. That R3, you can take any two-dimensional plane. Like pick two directions, it defines a plane, right? You can then project that down to the surface using what's called the exponential map. It's just geodesics going in that direction. I mentioned it one time before. And you get a two-dimensional submanifold of your three-dimensional manifold. That two-dimensional submanifold has a Gauss curvature. Okay? Now, what if I said, what's the average Gauss curvature over all possible choices of two-dimensional submanifolds? Just average over all of them. The average Gauss curvature, that's the scalar curvature. Okay, so if you just average all possible two-dimensional Gauss curvatures, that's what scalar curvature is. And so, not surprisingly, this three-dimensional metric has something special about it. What's special about it? The scalar curvature is 0 everywhere. And since the scalar curvature is 0 everywhere, you know, it's not surprising that when you say, look at all spherically symmetric three manifolds that have 0 scalar curvature everywhere, it's not surprising you're getting something reasonably beautiful out. By the way, what has 0 scalar curvature? Well, R3 has 0 scalar curvature. You all see how this is asymptotic. Started out sort of like R3 there, right? And this is also has 0 scalar curvature because it's asymptotic to R3. And so the fact that, you know, we knew that this thing was going to blow up and become really big, but in fact it becomes really big in the same way that it was already big on top. Because why? These things both have 0 scalar curvature. So it's like two R3s connected by a net. That's what you get. Topologically, by the way, it's still R3 minus the origin, right? So what we're going to do is we'll do this on, you gotta take out the origin where x, y, and 0 all 0. Okay, in fact, you can make this even more precise. Turns out, if you want to visualize this metric exactly, it turns out it's a rotated parabola. This is exact. So now what I'm going to do is I'm going to go to, I'm going to have a W as a fourth dimension. This is not T. It's not a space-time. It's just four-dimensional Euclidean space. And let's have this be X. Let's have this be Y and Z. And now let's take a parabola. And this parabola has the equation that if you take the square root of x squared plus y squared plus z squared, which I'll denote this. This is the length of the vector x, y, z, but that's the square root of x squared plus y squared plus z squared, right? And so what's the equation for a parabola? Well, you gotta turn your head to the side a little bit, right? But we're going to say this is equal to w squared over 8m plus 2m. That's a parabola which you then rotate around in four-dimensional Euclidean space. And if you do that, this the induced metric on this rotated parabola is in fact the Schwarzschild metric of mass m. Okay, so this is four-dimensional Euclidean space. And now you can see, oh yeah, that parabola is kind of looking like R3. Like if I take a curve and rotate, by the way, each of these is rotating around an S2, right? Because this is a three-dimensional space here in the W equals 0 plane, right? And so that's an S2. This is an S2 right here, right? And so you have a family of S2s that makes sort of R3 at infinity, right? And then we have an R3 here, and they're connected by a neck. And it's this, or I guess you could call it a paraboloid, but it's not rotated in the usual way. Normally I rotate a parabola this way, right? We're rotating it around that way, so it's a kind of paraboloid. Okay. Any questions about this? So now what I'm going to do is imagine, so now this is explicit. This is something familiar because it's inside of R4, right? This is, we call this the Schwarzschild metric sitting inside of actual R4, right? It's quite explicit. But now what I'm going to do is when I draw this picture, when I draw something like this, I actually mean that the top part of this paraboloid, okay? But then let's put in any metric you want in here, okay? And so that would be an example of a slice of a space-time. I'm going to draw this a little bit better. See here. And what I'm saying is, let's suppose that we have a three-manifold down here with some metric G. And let's suppose that's exactly Schwarzschild outside of some bounded region. And so Schwarzschild of mass M, okay? Now, why would I want to do that? Well, it's because if I know it's exactly this Schwarzschild metric of mass M, then I know it's exactly this. I know what the total gravity of the system is. I know what the total mass of the system is because I know how geodesics curve in the space-time. Do y'all see that? And I can say, oh, okay, it's just like Newtonian physics as if the total mass is M. So when I say something is Schwarzschild of mass M at infinity, I know what that means. What that means is that the total, this is what we call a total gravitational mass. In other words, is M, okay? And so it's the total gravitational mass of this slice of a space-time, meaning if I get really, really far away from the center, gravity is going to be pulling me in as if the mass of the system is M. Okay? Now it turns out, remember I said the Schwarzschild has scalar curvature equal to 0? Turns out scalar curvature, remember matter curves space-time, turns out in this context, scalar curvature is matter density. Okay, it really is that number. Like if we're assuming something here, we're taking a t equals 0 slice so that there's that sort of everything, we're taking a slice of a universe where everything's at rest. So there isn't momentum density and pressure that's relevant anyway. There's just a matter density. And that matter density is the scalar curvature. And it's 0 for a slice of a black hole. Now why? You might say, wait a second, but a black hole is not a vacuum. Why would you want 0 matter density in the case of a black hole? Well, it's because all the matter has already fallen into the black hole. Right? The black hole itself has mass. But yeah, in the past, a lot of matter fell into it perhaps to form it. But the scalar, in fact, it's vacuum. Okay, so a black hole is a vacuum solution to the Einstein equation. Okay, so we're assuming that you have a t equals 0 slice of a space-time. Total gravitational mass is m. And then if you want to be physical about it, that means the scalar curvature everywhere must be greater than or equal to 0. Why? Because we don't observe negative matter density in the universe. Okay, so let's suppose now that we fill in with non-negative scalar curvature. Okay. Now this might seem a little familiar. Remember that Gauss-Bonnet theorem problem we did at the very beginning, right? Suppose the mass was 0 out here. Well, that's flat R3. Then if you want to fill in with non-negative scalar curvature, the same thing is true. There's only one way to fill it in, and that's just the flat R3 metric. Okay, that's still true, even for this more complicated notion of scalar curvature. Right, and that's true in all dimensions, by the way, not just 2 or 3 dimensions, but in all dimensions. But now here's where it gets really cool. You guys ready? I'm going to show you. I suppose it might be my favorite theorem in mathematics, but I am biased.
I think we've gotten a bunch of those.
I mean, okay, what's my favorite theorem in mathematics? I mean, I really do think, okay, the generalized Stokes theorem is, I call it the central theorem of mathematics. If I had to pick one theorem at the center, it's this generalized Stokes theorem, okay? So learn that. Maybe my first favorite theorem in mathematics might have been the Gauss-Bonnet theorem. That's pretty cool. All right, that's like my first favorite theorem. All right. And then my second favorite theorem might be the positive mass theorem. And that was proved by my thesis advisor, which is why he was my thesis advisor. It's like, you're cool. All right? let me learn from you. And I'll tell you what the positive mass theorem here in just a second. And then my current favorite theorem, I don't claim it should be your favorite theorem, but I'm going to show it to you right now. And it's a theorem that I proved, and I'm completely biased. Okay, completely 100% biased. I'm not saying it is the best theorem in mathematics. I'm just saying, yeah, I'm really proud of it. It's like something I did, and I enjoy it for that reason. So I guess, yeah, I suppose it's my favorite theorem, I suppose. Right? Because I spent my life thinking about it. Right? I mean, that's fair, right?
Yes.
Yeah. Okay. So, and it's pretty cool, too. All right. Okay, so what it's, so in 1973, Penrose published a paper where he made the following observation. And he noticed that, suppose you have a slice of a space-time, such as this picture I've just drawn. Suppose it has, he didn't say it's Schwarzschild of he said the total gravitational mass is m. So in other words, suppose it's exactly Schwarzschild outside of some bounded region, okay? Keep it simple for demonstration purposes. And then he pointed out, let's suppose that you have some minimal necks here, and then you have a minimal neck there that has area A1 and that has area A2. Keep in mind these are these are S2s here, right? These are two spheres. Everything's one dimension higher than drawn. Now these turns out those represent black holes. So you have a black hole here and a black hole there, okay? And so why does it represent a black hole? Let me just not say right now, okay? But it turns out things that locally minimize surface area are black holes. Okay? And you see that here, by the way. This right here is the horizon of the black hole. Horizon. I failed to mention that. But and those coordinates over there, this horizon, that S2, is exactly this horizon here, this S2 that happens at r equals to m over 2. Okay? Okay, so maybe by analogy, extension. Well, what's the mass of the black hole? Well, over here, if you look at the Schwarzschild and you say, hey, what's the area of this black hole? You can plug into this formula, and what you find is that the area of the black hole here is equal to 16 pi m squared. Okay, m is just some parameter in the Schwarzschild space-time mass m. You do the computation. You plug in here r equals m over 2. That gives you a 1 plus 1, which gives you a factor of 16 here. And then you plug in 4 pi r squared times with the radius m over 2, do the computation, you get area equals 16 pi m squared, it turns out. Okay? And so then Penrose argued that if you have two black holes of area A1 and A2, and if you look at the total area A, so A would equal A1 plus A2, that the mass of the black holes should be, that they contribute in total, should be the total area divided by 16 pi. Okay? And so that's the mass contributed by the black holes. Then you have the total gravitational mass of the system. And so his argument was, if general relativity makes any sense at all, the total gravitational mass of the system should be at least the mass of the collection of black holes. So therefore, m should be greater than or equal to the square root of a over 16 pi. Now what's cool is we have a geometry theorem here. Forget physics entirely, right? What it's saying is, suppose that you have something that is Schwarzschild of mass m, outside of, what does that mean? It means this metric right here in the box. It means this rotated parabola, right? Suppose outside of a bounded region, it's exactly Schwarzschild of mass m. Then fill in it however you want with non-negative scalar curvature. Why? Because this is matter density, right? And we're assuming the matter density is non-negative because that's a physical assumption. But furthermore, if this truly is the mass of the black holes, the square root of a over 16 pi, which Penrose waved his hands as a physicist sometimes do to argue, right? Okay, that it seems like it's true for a Schwarzschild black hole. Okay, so if this is the mass contributed by the black holes, and you have non-negative energy density everywhere else, then the total mass of the system should be at least the mass of the black holes. That was the argument that he made. But now we have a geometry statement, or you might call it a geometric conjecture. In fact, this is known as the Penrose conjecture. And it's saying the mass of a system is greater than or equal to the square root of a over 16 pi, where a is the total surface area of the horizons of the black hole, and you're assuming non-negative energy density in the space-time. And so he made this conjecture in 1973. And my thesis advisor in 1994 suggested I think about this. And so I did. I came up with some partial results, got me some good jobs and everything. But as I was graduating, I think I may have already told you, I had some competitors who actually proved this inequality. They're named Gerhard Husken and Tom Illmanen for a single black hole. And they used the geometric flow technique to do this. And then I was a postdoc, I graduated with my PhD, and I was really impressed with their techniques. And then I thought about, okay, is there another way to approach this problem? So I came up with a geometric flow to study these types of three manifolds. And I was able to prove the inequality for any number of black holes. And both of our papers came out in 2001. I mean, their paper predates mine, but they both appeared in 2001. And so, anyway, this was what we were able to prove. So that's now. What did my advisor prove before me? By the way, what was he famous for, among other things? But that's my favorite work of his. This is Richard Shane with Jingtong Yao. They proved that m is greater than or equal to 0. This is known as the positive mass theorem. M greater than or equal to 0. So this is known as the positive mass theorem. m greater than or equal to 0. It's just saying, hey, fill in however you want. The m is always greater than or equal to 0. And by the way, that's kind of analogous to our Gauss-Bonnet theorem we were talking about before. Remember, and I never, because we don't really have a Schwarzschild metric in lower dimensions. It's really just ends up being a cone. And but basically, in dimension 2, the total mass is just the integral of Gauss curvature. And it's just the integral of energy density. So of course it's greater than or equal to 0. But in higher dimensions, it's actually quite non-trivial. It's quite non-trivial to show that if you have a Schwarzschild of mass m, and then you fill in with any metric you like with non-negative scalar curvature, then this m must be greater than or equal to 0. And furthermore, if m equals 0, it's flat R3. That's it. Okay, and that was that rigidity statement we were talking about before. And so all I did, and somewhat, and the reason it was natural for me to have the advisor I did is, of course, he was like, hey, we already proved m greater than or equal to 0. See if you can prove m is greater than or equal to the square root of a over 16 pi when you have these minimal surfaces inside. So what else can I say about? Yeah, question.
So I'm an engineer.
Yeah.
What's happening with the units? And m is greater than a over 16 pi.
Turns out what I'm doing here is I'm setting two things equal to 1. One is the speed of light equals 1.
Okay.
Now, if I were a physicist, I would have c's all over the place here. They'd talk about c's and c squares, the c to the fourth, and all that stuff, right? And I just like, let c equals 1. Why would you do that? Okay, as far as I'm concerned, the speed of light equals 1. The other thing that I'm setting equal to 1 is the universal gravitational constant. So remember, when you say the force of gravity, right? The force of gravity is equal to, m1, m2 divided by the distance between them squared, right? But then there's some constant here to convert between the units.
Right.
That equals 1 as well. Okay?
Yeah. Great.
And so when you set both of those things equal to 1, then it turns out that mass has units of length. In higher dimensions, it's if you're in n plus 1 dimensional spacetimes, mass has units of length to the power of n minus 2. But we're without n equal 3, right? So mass has units of length for us. Yeah. Because, and by the way, you can conjecture this is an equality in higher dimensions as well. Because who's to say we live in a 3 plus 1 dimensional spacetime? What if some other people live in an n plus 1 dimensional spacetime? Then in fact, mass does have units of length to the n minus 2. And with a co-author here at Duke, there was actually a postdoc, Dan Lee, who was here for a while, 3 years. He's a professor in City University of New York, Queens College now. And we proved the same inequality in higher dimensions as well, up to and including dimension 7. So let's see here. Other questions? So next time, what we're going to do is, we can see there's all kinds of fun to be had, but you're probably wondering, what exactly is scalar curvature? You haven't told me exactly. I told you it's sort of like an average Gauss curvature. Okay, so we need to do that. And also we need to understand, okay, here are metrics, but what is this? How do you even define what a geodesic is, right? How do you take the covariant derivative of a vector field in the direction of another vector field? And it turns out that's the next thing that you guys don't know that I need to show you, right? And so first we get the idea of what a metric is. Then we're going to learn how to take the derivatives of vector fields in the direction of other vector fields. And it turns out once we do that, then we can define what curvature is, abstractly, without a third dimension. And it's going to generalize the notion of Gauss curvature. And it turns out we're going to be able to do everything intrinsically. And we won't have to refer to a third dimension at all. So it's kind of a cool, exciting thing to do. Okay, see you guys next time.